Welcome to the CSET March webinar. Presenting today will be Dr. Vinod Vasudevan. He is an associate professor of civil engineering at the University of Alaska Anchorage and has served on the faculty of the Indian Institute of Technology, Kanpur. His areas of interest include traffic safety, non-motorized road users, technologies in transportation, and infrastructure financing. He will be speaking to us today on tracking non-motorized road users using LiDAR. And I'll turn it over to you, Vinod.
Thank you, Vicky. Yeah, so welcome to the CSET March webinar. Today I'll be talking about tracking non-motorized road users using LiDAR. Yeah, this is the presentation overview. I'll start with the significance of tracking non-motorized users, and I'll give a brief introduction to LiDAR and some of the applications in LiDAR. And I'll end up with some of the sample application. I'll only cover two, which is pedestrian crossing behavior and bicyclist safety. So first question, why do we track non-motorized users? Of course, they are the most vulnerable road users, and we all know that if you are following traffic safety, we all understand that since they don't have any protection, they are one of the most vulnerable road users. And recent statistics show that these non-motorized users, mainly bicyclists and pedestrians, they account for about 20% of traffic fatalities in the US. That trend is same for almost all the previous years also. So, which again, keep in mind that 20% is a huge number, because if you look at the mode share of pedestrians and bicyclists, it's very less. So 20% is disproportionately higher. Now, typically we use video data and manual observation to track non-motorized users' behavior, like where we observe, what pedestrians do, like where do they cross, and where do they cross, what do they do, how long they wait. So video data has been used extensively, and many times where video data cannot do the job, we may deploy some manual observation. Now, the thing is that when we are going to the connected vehicle era, tracking vehicle trajectories become very important, because we need to, maybe the technology will evolve over the years, and technology already exists to track the vehicles. Now, tracking trajectories of non-motorized users also is extremely important. First of all, it helps us to understand some of the behavioral aspects, and which you could not capture using the traditional methods. And also in a connected vehicle era, pedestrian and bicyclist movements are extremely important, because they also play a part in the safety and mobility, mainly in safety. So unless they are connected, it's very difficult to track them. Okay, especially due to the sudden changes in direction and speed of non-motorized users, especially pedestrian. Tracking them is very challenging. At the same time, they are extremely important. So LiDAR, maybe many of you know what LiDAR is, but still, just to give an overview, LiDAR stands for light detection and ranging, and it uses light in the form of a pulse laser to measure ranges. The advantage is that it measures the distances at high accuracy. That's a major advantage. Now, since LiDAR collects data at high frequency, you can go up to 50 Hertz, even slightly higher if you have a high resolution LiDAR. Now, once you have a high frequency data, then it can generate a 3D information of an object and its surrounding. And traditionally, they have been used extensively in land surveying, asset management, forestry and farming, mining, etc. There are so many applications which are documented, and you may be familiar with it. If you're not familiar, if you just go search online, you'll get so many applications. Now the question is, how can we apply LiDAR in traffic engineering? Again, it is already used extensively in the autonomous vehicle. Again, this is not an image, I got it from website, some other website. I cited the source. Basically, the idea is that once you have a LiDAR, since it provides the point clouds, if you apply proper algorithm, you can get all the details, like most of the details, like, you can detect other vehicles, you can detect the static object and dynamic objects around the LiDAR. So once you have the information and once you have the data at a high frequency, you can use it to measure various things. So we'll discuss some of the applications. So they're already used in autonomous vehicle. Most of the autonomous vehicle, I think, except for Tesla, they use LiDAR. They use LiDAR as one of the major sensors. So with proper processing, we can recreate the traffic condition using LiDAR. Speed and position of vehicles are essential, not just vehicle, any objects are essential for traffic engineers. So if you can give me the speed and position of an object over a period of time, as a traffic engineer, I'll be very happy, because that's the information I want to estimate various parameters like, density, speed, flow, etc. So LiDAR's capability to measure distances precisely offers a huge potential to traffic engineers. However, there are challenges. We'll discuss them. Now, to collect these data to measure these distances, there are two options. One is to go with a stationary unit. You are using as a static kind of a LiDAR unit, and then just like a video camera, you'd be very site specific, where you are capturing the information of a particular region. It can be intersection, it can be a mid-block, etc. Another option is to use as a mobile unit. That's what I'll be focusing on in today's presentation. So when you use it as a mobile unit, first of all, you can get more naturalistic data. Second thing, they are not site specific. So again, there are advantages and drawbacks of site-specific versus non-site-specific. I'm not going into those discussions. The objective of this presentation is to show an application, like how can we use LiDAR for non-motorized user applications. So when you are using a LiDAR, it has to be an instrumented vehicle. So when you have an instrumented vehicle, you can analyze or you can capture the behavior of road users, including non-motorized users, more realistically. So, of course, you can collect some naturalistic data, but to collect the naturalistic data, we need to first develop an instrumented vehicle, collect and extract data from naturalistic driving studies, and analyze the data that you collected. Although developing instrument vehicle looks very tricky, but they are not very difficult. I'll discuss that. So we need to, when we have an instrument vehicle, we need to collect the data on static and dynamic objects, the geometric features of the road, or the road user behavior. Again, all these data should be captured concurrently. So again, this is an option, major instruments for an instrument vehicle. Again, there can be various other sensors, but in my opinion, these are the best way to capture. One, you need a LiDAR, because LiDAR has a lot of capability, especially measuring distance. Video camera, on the other hand, okay, LiDAR advantage is that it can measure distances, but to detect an object, video camera may be a better option. So if you have a LiDAR and video camera, you can use them together to get a better idea of the objects around. Then we need a GPS unit, because if the vehicle is moving, you need to estimate the location, and hence, once you know the location, high precision location, you can estimate the speed and also location. Then if you have an OBD sensor, you can extract the speed from the OBD sensor. So once you know the speed of the instrumented vehicle, if you know the relative location of the surrounding object at the high frequency, you can estimate the relative speed of the surrounding object, and then you can estimate the actual speed. Okay, so this is an instrument vehicle we developed in UAE. As I said, I mean, developing an instrument vehicle, it's tricky, but it's not that difficult. So what we have is, I'll show you a picture. So this is the LiDAR, and then we have cameras, and these cameras have lens, which so with a proper lens, we can capture, with 4 cameras, we can capture a 360-degree view around the vehicle. LiDAR also captures 360-degree data. Then you need some kind of a data acquisition system, because all this data, LiDAR doesn't have an internal memory, and also so the data has to be captured in a computer. And yeah, this is the LiDAR camera, and these are 2 computers which is powered, and we have a router, etc., to collect data. So this captures LiDAR data, and this captures the video data. Again, there can be different arrangement, but this is a simple arrangement, and it wouldn't cost a lot of money. So the main sensor is LiDAR. It collects point cloud of the surrounding at a given frequency. I mean, you can decide the frequency, but in this case, we use 20 Hertz. And if you, as I said, if you have a high resolution or advanced LiDAR, you can even go with a higher frequency. So again, 20 Hertz means that you are capturing data 1/20th of a second. So that itself is sufficient for most of the traffic application. But if you want a higher resolution, you can always choose it. So we used Velodyne VLP16. We also have VLP32, but we used VLP for this particular application. So for this particular vehicle, it has 16 channels, which means there are 16 beams which are there. The range is 100 meters. Accuracy is plus or minus 3 centimeters. Again, this is what the manufacturer says, and we kind of validated it. They are very good. Field of view vertical is 30 degree, means it's just 15 degree here, 15 degree here. That's a vertical angle. Now, of course, horizontal angle is 360 because it captures the data all around. So 30 and 360. Again, these will vary depending on the sensor we are using, but they are typically the same range. So when you compare, I mean, just a quick comparison between LiDAR and video data. In LiDAR, we collect point clouds of an object within the range, whereas in video, we capture images. Okay, frequency is up to 20 Hertz. Again, this will vary depending on the LiDAR, and video camera typically captures 24 frames per second for high definition video. Field of view is 360 degree and 40 degree vertical. The reason I say 40 is, although I mentioned 30 degree, that is from bottom and back. So when you get the effective field of view would be 40. Okay, you can get up to 90 degree cone with wide angle lens. So object detection, we need data processing. It's a time consuming, whereas video camera with all the recent developments in image processing, it's very easy to detect. I mean, there are so many programs available free to use it, but for object detection in LiDAR, it needs a lot more processing. This is where the interesting thing is distance data. In LiDAR, of course, they are readily available, whereas in video camera, you need data processing. But still, if you want to measure the distances, you need at least two views from 2 different cameras to measure the distance. So when you look at it, the major point is that object detection is easier using camera, whereas distance is easier when we are using LiDAR. So if you can blend them together, you will get both object detection and distance data. That's why the camera and video camera and LiDAR are kind of essential too. So to collect data, we have to take the vehicle and drive in the study region. And by having a proper data acquisition system, they will collect the actions of various road users. These include the driver of the instrumented vehicle, because you can see when a driver is accelerating, when he's decelerating, when he's changing lane, etc. Also, we can capture other road users like the pedestrians on the street, the bicyclist, and the drivers of the other vehicle. Again, that's an interesting thing, because just like any other object, drivers of other vehicles are also other objects. So by capturing high frequency data, we can estimate what other drivers are doing. Are they accelerating? Are they decelerating? Are they changing lane, etc.? So that is another interesting aspect. And so these data are extracted in appropriate format. Again, I'll show you some of the LiDAR data. So this is, again, once you capture the data, this gives a top view, and you can see some of the vehicles moving, etc. But once you look at this is a different angle, same data in a different angle. Now clearly you can see, okay, these are some pedestrians. This is some vehicles. This is a bus. It's a busy intersection. Again, this data is from India, not from US, so that's why you see some of the three-wheelers also. There's a lot of pedestrians. And one thing I want you to look at is, again, I will go back to this video. So, okay, this is something I want to look at it. See, when your bus comes, you see this area behind it. That's an occlusion, because we'll discuss that in the coming slide. Because since it's light rays, so once you have a object, then it occludes anything behind it, because light cannot pass through an object, obviously. Okay, so that's kind of a view. Now, when you look at it again, when you look at the LiDAR, it's a static image. These could be roadside vegetation. That could be, in this case, that could be a truck or a bus. This could be a car. This could be bikes, etc. So the question is, how would you detect them and track them? Some of the challenges is detecting objects from point cloud is challenging. So shape of an object changes based on the distance and angle. For example, if you are looking at a vehicle like a car from a LiDAR, if it's at 90° or right in front of the LiDAR, it may be looking like two rectangles, one at the windshield and the other one is in front of the engine. Whereas when you look at the side view of the vehicle, the same, it is a sedan, you'll be seeing the profile, and they look very different. And keep in mind that then the vehicle, as the vehicle moves from front to side, the shape would be changing. So that's a challenge you have to deal with, and you have to develop some algorithm. Other one is occlusion, as I showed before. Whenever you have a object which is slightly larger, it will since light cannot pass through, it will you cannot see the object behind it. So in some cases you have to again keep in mind of those issues, and you have to especially if you are observing something behind it, so you have to make some assumptions. Major challenge is these point cloud do not have unique IDs, because at each time frame you are getting a point cloud, unlike GPS, where GPS the same unique ID is maintained over time. Here it's starting a fresh scan every 1/20th of a second. So you have to develop some algorithm to track this. So tracking these points over various time periods becomes difficult. So you need to develop algorithms first to detect and to track objects. Okay. So first step, I mean, there are so many points, so we can remove some unwanted points. So let's look at this example. So here, for example, let's say I'm interested in pedestrian. This is another mid block. Okay, I know that based on my observation, these are pedestrian, but there are so many things. So how would you know that these are pedestrian? And if you are analyzing the pedestrian behavior, we don't want anything about this, let's say the vehicles or any vegetation, then we can deploy something called filtering. Again, filtering is a simple concept. What we say is that we know the properties of pedestrian. We know that pedestrians have a particular height. You can give a range of height and particular size like width. And we also know that pedestrians are only on the main roadway. They won't be on the sidewalk. I mean, they are on the sidewalk, not on the main roadway. So by putting those kind of a restriction, once you put those filters, same thing we can apply. So here, when I apply an algo like filter, then we can clearly see this pedestrian. There are two pedestrians here, one pedestrian here, another pedestrian here. So by doing it, we are reducing the size of the images. For example, the previous image, we had around 21,000, like totally 22,000 points, whereas here we only have 45 points. Again, keep in mind that this is for one time frame. So when you look at even for a minute, you have to multiply it with with 20 times 60. So that's the size we are dealing with. So this is a big reduction, and it will help us to do that. So again, I showed only pedestrians. So similarly, you can apply some filtering for, let's say you are interested in only cars. You can apply those algorithms or those kind of filtering. Okay, so now second question is, how do you detect? So since point cloud do not have unique IDs, we need to write programs to detect and track objects across various time frames. So there are various data structures like such as quad tree structure, etc. we can use to detect object. Again, you can also use the video data to help you detect object. That's what we are working on right now, but it takes some more time, but that would be the easier way. Still, even if you detect using video, you need to detect the same thing on LiDAR data also. So we used DB scan, which is a cluster-based technique. So we use DB scan. To implement DB scan, we wrote program in Python. Again, then DB scan has two parameters, epsilon and minimum points. So what I mean by that is, let's say basically DB scan does this in simple terms. It will take 1 point, and based on the radius we give, it will scan for all points around it within that radius, and then see whether that satisfies the minimum points. Okay, so for example, for a car, in our case, we used an epsilon as 1.25 meter and minimum points as 50. So what it means is that whenever around a point, if you have at least 50 points within 1.25 meter range, then that will detect as a car. Again, this is something worked for us. For bike, we determined that to be 0.5 meter and minimum 10 points. Again, that varies based on the LiDAR you're using and the scenarios. I mean, for example, if you have a slightly different kind of environment, that may be different, but that's something you have to figure out based on the LiDAR you're using and your application. But in our case, these work for us. So similarly, we had some other set of parameters for pedestrian. Now, the second thing is that, again, here we are only detecting an object. Now we are detecting object. We detected object at various time frame. Now the question is, how would you track them? To track it, we need to see where an object is over different time periods. So let's look at this example. Let's say we have three vehicles. I mean, in this case, vehicle 1, vehicle 2, vehicle 3. The same thing can be applied to pedestrian, but to illustrate, I'm just using three vehicles, and this is nth time frame. Now, when you look at n+1 time frame, n+1 time frame, we may have similar, like three vehicles, assuming that no other vehicle entered to the frame. Again, for a simple case. Now let's say there are still three. So how do you know if this is vehicle 1, this is vehicle 1, or this is vehicle 1? Because they don't have any unique ID. So that's the challenge. Computer doesn't know. Okay. So what we can do is, we can, I mean, again, as a simple logic, what we can say is that once we know the speed of the vehicle, we can estimate the speed by looking at the previous frames. We can apply some simple calculation. We can estimate the speed. So based on the speed of this vehicle, we can estimate again, keep in mind that n+1th frame, we are talking about 1/20th of a second time. In 1/20th of a second, how far can this vehicle go? So we can create a kind of a region where this is the region where this vehicle can maximum go. What it can do is it can maybe accelerate at maybe maximum acceleration, or it can completely stop. Okay, and also similarly, it can go laterally. So once you know in 1/20th of a second what would be the range, we can define this kind of a zone. And we can say that if I see an object within this particular rectangle, in this case a rectangle, but it can be any other shape. Okay, this is for illustration purpose. We use rectangle, but some people use ellipse. It's up to you. But what we are saying is, if you see another object within this rectangle is formed based on this property. So when you say that, if you find anything within this rectangle, that there's a high probability that this would be a vehicle 1. It cannot be vehicle 2 and vehicle 3 because their influence area would be way far. Okay, that's how you then similarly you do it for each time frame. Then once you do that, you will have the position of the vehicle. You are tracking a particular vehicle across various time frames. So this is only for vehicle 1. Similarly, you have to do it for vehicle 2, vehicle 3, etc. And when you have a busy frame where you have so many pedestrians, so many vehicles, you have to keep on doing the same thing. That's why it's time consuming, but you get a lot of data. Okay. Now, once you, as I said before, if you collect the data, when you carry out data collection, it can capture the side vegetation or any other object on the side of the road. We can detect other vehicles, other cars. If there's a pedestrian, they can detect too. So when you collect data, there are two types of data that we can get. First is the user behavior of the driver of the instrumented vehicle. Let's say we have a driver there, and whatever he does based on a certain scenario. Let's say when he sees a vehicle in front of it, what does he do? Is he decelerate? Does he decelerate immediately, or he goes closer, etc.? Again, those kind of studies are important for car following behavior. That data may be captured. Or when he sees a pedestrian, what does he do? Does he stop? Does he yield, etc.? But as a drawback, one of the drawback is that people can say that the driver may be biased, because since the driver knows that this vehicle is instrumented with some sensors, there is a chance that they may drive differently. Other one is, by using this one, you can capture the behavior of other road users, including other drivers. And the chance they will be unbiased because they have no idea. They may not have an idea that they are being observed because you have a vehicle, but they don't know. So this would be so this data would be better, but we did some analysis and we have some proof saying that after driving a vehicle for a particular duration, the driver don't really, they will just follow their natural instinct. They won't really, maybe after 10-15 minutes, they just drive the way they naturally do. But again, that's a totally different discussion on a different day. But so some of the sample applications, it captures relative locations of objects around at high frequency. Now, once we have the relative location, we can estimate the relative speed with respect to the LiDAR or the instrumented vehicle. Once we know the speed of the instrumented vehicle, we can calculate the actual speeds. Some of the sample application, as I mentioned before, one is pedestrian behavior and bicyclist behavior. And we also did some driver behavior, but I'm not discussing that here. We are only discussing a couple of them. So in pedestrian crossing behavior, the objective was how the behavior of pedestrian vary on a mid-block crossing with respect to vehicle type. That was our objective. What are the factors that affect the change in crossing behavior? So what we observed is that we mainly categorize data into two. What happens when the vehicles are observing in front of a car and in front of a motorbike? I must admit that this is the data based on my work in India. So these are India. That's why you have so many motorbikes and so many cars. So again, the results are not important, but the idea is that it can capture the details. Like the results shows that the walking speeds of pedestrian changes significantly in front of a car. So that this in front of a car, they walk at high speed when they are at the middle of the crossing. This is the crossing, completion of crossing. This is the start, this is the end, and this is the middle. Whereas when they cross in front of motorbikes, again, we tested it at various speeds. But when they are walking in front of motorists, their motorbikes, their speed is more or less constant, which is interesting. And in another study, again, this study is published in Traffic Injury Prevention. And another study, what we did is we also tracked their path, like trajectory. So when you track their trajectory, this shows this. I mean, we expect a pedestrian to cross in a direct path because that's what, and those are the path we estimate when we use the parameters like post encroachment time, etc., PET. Now, what we observed is that in reality, pedestrians walk. They don't walk in a straight line. They just go either away from vehicle or towards vehicle. If they are walking away from vehicle, that's still okay because as from safety perspective, they are getting more time. They, in the sense, both pedestrian and the motorists are getting more time. But if they are walking towards the vehicle, that kind of reduces the time that the driver has to react, which is dangerous. So in some cases, pedestrians walk as much as 5 meters towards the vehicle. Again, those values are significant. The idea is that, I mean, we can see what are the application, we can argue about application, but the idea is that LiDAR can capture these kind of details, which have a lot of value in the safety and mobility applications. In another application, what we saw, some of the results of the maximum speed attained by a pedestrian at, these results are not important, but 70% of the pedestrians took high-risk trajectory in front of motorbikes and 50% in front of cars. Severity of an event, I mean, we all know that the proportion of severe conflicts were more in motorized bike pedestrian interaction. That is again interesting because we expect one of the reason could be that since the bikes have a small kind of front face, so pedestrian may be taking higher risk, assuming that they cannot cause any serious injuries. So in another objective, another study on bicycle safety, what we did is our objective was to study the lateral passing gap of bicycle and motorized vehicles on Indian roads. So guidelines in Canada specify that there should be a minimum safe gap is 1 meter or roughly 3 feet. So the idea was to see whether on Indian roads they are leaving that gap. So we drove the instrument vehicle around Kanpur, is a city where I lived before. So we collected data for around 6 hours, and the roads have, the streets are highly congested. So in 6 hours, we covered only like 110 kilometers, which is roughly 70 miles. And we covered that in 2 days. And this was in city limits. So, and this is what it shows. So passing distance, this is a lateral passing distance, and this is the speed. So this is a motorized two-wheeler, this is a motorized four-wheeler, and these are heavy vehicles. So if you can see that, irrespective of the speed, if the speed of the vehicle from two-wheeler, they maintain passing distance, lateral passing distance is more like there are so many vehicles within 0.5 and 1 meter. 1 meter. Okay. So, oh, sorry, this is actually, this is 1 meter. Yeah, that's true. Sorry. So summary of data, we had around 300 bike vehicle interaction. Again, keep in mind that the vehicle in all the time are not necessarily the instrumental vehicle. They are also other vehicles. We had different categories on various road types like divided, undivided, arterial, highway, and some of the roads had bike lanes, some of them didn't have. So we had all this categorization, and we are not discussing the details here. But the results showed that lateral gap is not influenced by speeds of passing vehicles, as we shown there, because speed was not a factor. Statistically, they are not factor, but they are influenced by road classification and vehicle type. Two-wheeler left a lesser gap, whereas heavy vehicle left more gap, etc. Most of the times, minimum lateral gap was not maintained. Again, from safety perspective, these could be, some of the findings that the policymakers can make. As I mentioned before, the idea was not to discuss the application rather than showing how LiDAR can be used to capture these kind of detail. So other applications include, LiDAR has been, again, static ones. LiDAR has been experimented to detect pedestrians at intersection, static. Similarly, LiDAR has been used to detect animals near highways and warn drivers. There are so many. Now, some other application is we can use LiDAR for faster CAB deployment by having an instrument vehicle capturing data of the traffic stream that can help capture information like, the connecting non-motorized users to make them connected. This is one of the ways, so you can do that. With that, I would like to acknowledge some of my researchers who helped me. One of them is Dr. Sean Butler, computer science faculty at UAA. Then Pupali Datta, she was a PhD student with me at IIT Kanpur. Rahul Soni, and these Rahul, Akhil, and Prakhar, they were my master's student. With that, I'm open up for any questions. Thank you. Any questions? It looks like there are no questions. So again, thank you very much for your time. And yeah, please feel free to contact me if you have any questions later on. Thank you.
Does anyone have any questions? Just post it in the chat.
No, I don't see anything.
Okay, well, in that case, thank you very much, Vinod. The next CSET webinar will be in April and presented by Ahmad Abdel Rashim of the University of Idaho, and information for that will be being sent out here shortly. And with that, thank you very much, Vinod, and I will stop recording.
Thank you.